Another important topic in space-time code is multi-input single output. So in wireless communication, to understand the operation of space-time code, we have to know what is MISO system, multi-input and single output system. So here at the here we have transmitter as well as receiver. By the help of spatial multiplexing, the transmitter consisting of is more number of antennas and receiver consisting of only single antenna. So that's why here generally let us assume here the transmitter consisting of two transmitting antenna and receiver consists only one receiving antenna. So that's why we are call it as multi-input and single output system, MISO system. This model can be represented with the received symbol Y. The received symbol Y will be represented by here in this diagram H1 and H2 are the two coefficients of transmitter 1 as well as transmitter 2. Now the received symbol Y is equal to H1, H2. It is a MISO vector. It is 2 cross 1 matrix. And X1, X2 is a transmitted vector. It is 1 cross 2 matrix here. It is 2 cross 1 matrix. And W is a Gaussian noise. Gaussian noise with mean 0 and variance is sigma square. Okay. Now the transmitted vector. So just now I said this is belongs to transmitted vector. This is multi-input single output system vector with coefficient, and in here it is a Gaussian noise. Now the transmitter vector X bar, the transmitter vector, it is represented with X bar. X bar is equal to here X1, X2. Here X1 is a symbol of transmitting antenna 1. X2 is a symbol of transmitting antenna 2. Let us assume here X denote a transmit symbol. Here we are assuming X is denoted as a transmitted symbol. Now the transmitted vector X bar is equal to 1 by H norm into this coefficient H1 star, H1 conjugate and H2 conjugate. It is a 2 cross 1 matrix with the transmit symbol, right? Here this entire part we are call it as transmit beam. Okay, this part we are call it as transmit beam. Now here H norm will be represented as under root H1 modulus of H1 square plus modulus of H2 square. The transmit beam, the formula of transmit beam is this one. Now, see here, I want to expand that one. X bar, that is transmitter vector, X bar is equal to, right? H1 conjugate by norm H into X and H2 conjugate by norm H into X. Here, for the transmitting antenna 1, value is H1 conjugate X by H norm, transmitting 2 antenna, H2 conjugate X by H norm. Okay. Now, here received vector, received symbol Y, the received symbol Y is equal to the coefficient H1, H2 of the transmitting vector. And here, see, I am and here the X bar is I am representing here, right? This is belongs to X1 transmitter antenna. This is belongs to X2 transmitting antenna. So this one I am written in the equation of this equation, this Y received symbol equation. I am putting X1 value as well as X2 value in that equation, the equation becomes y is equal to h1 h2 is h1 conjugate and h2 conjugate into x by h norm plus w, right? Now y is equal to, if you see here, the multiplication of these two matrices here, h1 into h1 conjugate plus h2 into h2 conjugate, we can represent it as, this will be represented as modulus or norm of h, right? Norm of h square. Here we know that h norm of h is equal to under root h1 square plus h2 square, right? So this is norm of h. Here the same vectors with conjugate, so that the resultant one of this one is mod h norm square. Okay. Now here I am putting this one. Here actually you will get the equation like norm h square by norm h into x plus w. Here the norm h and 1h is cancel. You will get the vector, received code symbol y is equal to norm h into x plus w. If you observe this one, this is a signal component and here it is noise component. Now if you find signal to noise ratio, the signal to noise ratio we can call it as signal power by noise power, right? So to calculate signal power, here I am making expectation of this entire term. So what is the signal component? Expectation of norm h, okay, into x, right? This is a expectation. So this expectation we can make it as, so it is an independent one, so it becomes h norm square and expectation of square. That is the signal power, right? Now this h norm square into expectation of x square by sigma square. Now see here, this entire term I am representing as power p of input vector x, input symbol x, right? So this is equation of signal to noise ratio. By using the help of this MISO system, we will discuss the operation of Alamouti codes. So this Alamouti codes is basically a space-time block code. Here it does not need knowledge of channel coefficient of a transmitter. That means beam of the transmitter, as well as hence it is very useful from a particular practical viewpoint. Now see here, consider a 1x2 MISO system. See here, 1x2 MISO system, it is, this one is belongs to receiving, the number of receiving antennas. The number of receiving antenna is 1. This 2 is belongs to number of transmitting antenna 2. Okay. And y is equal to is here the symbol received symbol y is equal to coefficient of transmitting antenna 1 and 2 into here it is a vector of transmitting vector. This is MISO system vector. It is transmitting vectors plus noise. Here x1 will be represented transmitting antenna 1, x2 will be represented transmitting antenna 2. This x1 and x2 are two symbols. Now if you see here, symbols received at the transmitting instant 1. So that is represented with y1. The symbol received at transmit instant 1, that is y1 is equal to h1 coefficient, h2 coefficient is multiplied with the transmitting vector plus s noise. Symbol received after the transmitting instant 2, here the transmitting instant 2, it is somewhat different with the transmitting instant 1. The transmitting instant 2, here it will get the first term is minus symbol with x2 conjugate and the second symbol is x1 conjugate. Now here in symbol received after the transmitting instant 2, this is belongs to transmitting antenna 1, this is belongs to transmitting antenna 2 for the second instant. Right? Now I want to expand this equation. Y2 is equal to, by multiplication, this 1 cross 2 matrix with the 2 cross 1 matrix, here you will get the equation like this one. Now Y2 conjugate is equal to, means Y2 conjugate means here you will get overall conjugate of this equation. So if you see here, H1 x2 conjugate plus H2 x1 conjugate plus W2. Here I am putting overall conjugate. Now if you see here, minus H1 conjugate you will get here. This conjugate and this conjugate will be cancelled plus H2 conjugate. Here you will get H2 conjugate into here x1 conjugate, this is x1 conjugate and conjugate will be cancelled plus W2 conjugate. Now I want to represent this equation with a matrix representation. Y2 conjugate is equal to, now see here, before writing that one, I want to put first my x1 term as first. Y2 conjugate is equal to, first I want to write x1 term, H2 conjugate x1 plus minus H1 conjugate x2 plus W2 conjugate. Okay. Now see here, Y2 conjugate is equal to, what is the x1 coefficient? H2 conjugate, and x2 coefficient is minus H1 conjugate, and here the transmit vector conjugate, transmitting vector plus here noise conjugate. I am putting as this equation as 2. It is the equation, I am call it as 2, equation 2. Now coming to the first equation, first instant equation I am putting here, y1. Y1 is my first instant equation, I am call it as equation 1. Now see here, this Y2 conjugate as well as Y1, I am putting in matrix format. This is, right, it is received symbol. Received symbol, that is Y1 and Y2 conjugate, and here this is MISO system of two instances, instant 1 and instant 2, right? It is a transmitter, okay, vector or transmit symbols, and here this one I am call it as W bar, this is noise vector. Now see here, this MISO vector, I am assuming this first row as C1, second row as C2, right? The C1 vector is equal to H1, H2 This is a column matrix, C2 vector, H2 minus H1 conjugate. Now the equation I want to represent, Y output vector or received vector. This is received vector. Received vector. Okay. This each one we are call it as a symbol. The combined one we are call it as a vector. Y bar is equal to here C1 X bar, right? C1 X bar and C2 X bar, right? So what I am doing here, Y1, Y2 conjugate, that is equal to, here I am putting C1 and C2 here, X1, X2 plus noise vector. So by writing the equation of this one, C1 X bar X1 and C2 X2 plus noise vector. Okay. Now here we have to observe the C1 Hermitius C2. Here I want to calculate C1 Hermitius C2 so that this space-time code is orthogonal or not. If the code is orthogonal, this code is called as a space-time block code, right? Now by observing C1 Hermitius, the C1 Hermitius, it performs first transpose operation, then conjugate operation, right? C1 is given matrix as column matrix H1, H2 conjugate. So here first I want to make it's a transpose, right? It's a transpose becomes here the transpose of this one H1 H2 conjugate, then conjugate. First here the transpose of that one is it becomes H1 H2 conjugate again conjugate, so that here you will get C1 Hermitius is equal to H1 conjugate H2, right? Now I want to substitute the value here. C1 Hermitius C2 is equal to, okay, what is the C1 Hermitius? This is C1 Hermitius value and it is a C2 value. If you multiply this matrix, here H1 conjugate H2 and H2 conjugate H1. So if you see, observe this one, here the resultant is 0. So C1 and C2, okay, two vectors are orthogonal. So this code is also called as orthogonal space-time block code. Now coming to its decoder operation, to find the decoding of this whatever the transmitted one, right? Here we have to observe, to find that one, here we have to calculate C1 Hermitius by C1 norm into received code vector Y bar, right? This is the equation of code vector Y bar, that is code vector Y, and C1, it is multiplied with C1 Hermitius C2. Now I want to expand this equation. C1 Hermitius C1 by C1 norm into X1 plus here C1 Hermitius with C2 by C1 norm X2 plus C1 Hermitius with okay error noise vector W bar by C1 Hermitius. Now here it consisting of some properties. C1 Hermitius C1, it is equal to square of C1 norm, and C1 Hermitius C2 is equal to 0. Okay, we can see here this is C1 Hermitius and it is a C2. If you find here the resultant value is, the vector value is 0. Now I want to substitute these two properties here, right? Here it becomes see, it is a C1 square by C1 norm square by C1 norm. It becomes C1 norm into X1 plus second one is 0, then here third one, right? And see here the resultant one, C1 norm into X1 and C1 Hermitius, this noise vector by C1 norm. Now this is signal component and it is a noise component. Here I want to find noise variance. Simple, the expectation of simple noise vector. Simple noise vector means the power of noise. The power of noise, we can represent it as expectation of this one. So generally the white Gaussian noise power is always variance into identity matrix. So it is always sigma square, right? And here this entire noise component I am call it as a W tilde. Here the expectation of variance of noise vector, that is W tilde is multiplied with W tilde conjugate. Now here I want to substitute this W tilde value, okay, in this one. The W tilde value is this one and second W tilde conjugate value is here, right? So these values are independent, okay, and the value of expectation of this one is, just now we know that is sigma square into I, okay, and it is also called as sigma square, right? And see here, now expectation of this variance of noise vector is equal to, just I am multiplying, just I am substituting the value of this one, okay, and here, and it is multiplied with C1 and C1 norm into C1 norm square and C1 Hermitius sigma square and C1. Now C1 Hermitius with C1 it becomes S, just now we are seeing property that becomes C1 norm square into sigma square by C1 norm. So the C1 norm square is equal to, it may cancel, you will get only sigma square. Now variance of noise vector is sigma square, okay. Now here the decoder value, that is C1 Hermitius by C1 norm into output vector or received vector is equal to, okay. Here this component we are already calculated and Gaussian output of noise, here we are calculated this one. This is signal component and it is a noise component. Now we can find the signal power by noise power. Signal power is equal to signal power by noise power. Simply we can written as signal power, that is C1 Hermitius square into, okay, the power of this one, the power of this one I am just call it as P by, okay, noise power, just now we are calculated sigma square. Now C1 norm C1 square, just we see here what is norm C1 square. Now this is C1 matrix, this is column matrix. C1 norm is represented like this one, okay. These are the coefficient of transmit vectors. So here I want to write this one as SH norm, okay. Now see here, signal to noise ratio is equal to Just I am replacing with the C1 norm with H norm. So here, because of power, it becomes square. So here H norm square, and expectation of this one, you can call it as a P by sigma square. So not P, I will tell you what is the value of this one. Now, see here, we know that the transmitter vector, it consisting of two symbols. Two symbols in each transmitted vector. The symbol that is the x1 for transmitter 1, x2 is the transmitter 2. So because of two symbols, we are using the expectation of x1 symbol. The power of x1 symbol is equal to the power of x2 symbol, so that here we will get the average power that is equal to P by T, P by 2. That is the half of the transmit power because of using two transmitting antennas. Now signal to noise ratio is equal to, just I am putting this entire value with P by 2. Okay. So now if you observe in the just now we have discussed the MISO system. It is same as MISO system extra this factor, right? Now here we have to see bit error rate of Alamouti code. The bit error rate of Alamouti code, this is signal to noise ratio equation. Okay. Here we can simply call it as this is signal to noise ratio of general one, okay, into off. So here bit error rate for high signal to noise ratio, there is a formula for this one. Bit error rate formula for this one is 2L minus 1 into CL into 1 by 2 into this is of SNR. Here into whole power L. L is our transmitting antenna. Antennas here, transmitting antennas are 2. So here 3C2, here L. 2 into L value is 2. 2 into 2, 4 minus 1, 3. CL, L value is 2 into 1 by this 2 and this 2 becomes cancel. You will get SNR square. Therefore, signal to bit error rate of Alamouti code is 3 by SNR square. Now, if you see here, we will do one problem so that you will easily understand the Alamouti code operation of block codes. Here, the question is given like the vector. The symbol y is given as, the received symbol y is given as 2 plus j and 1 minus 2j. So this is h1 factor or h1 coefficient, it is h2 coefficient. It is a transmitting vector x1, x2 and noise vector w, right? First transmit period I am representing with y1, symbol y1. And here W1. Next, during second transmit period, just now I said in second transmit symbol, here first you will get x2 conjugate with minus, and second one it becomes x1 conjugate with the noise component is W2. Now I want to expand this one with this equation. So see here, this entire row is multiplied with this column, you will get like this. Okay. And here, again, I am calculating y2 conjugate. So y2 conjugate means what? Here you will get y2 conjugate means minus 2 plus j x2 conjugate plus 1 minus 2j x1 conjugate plus w2 whole conjugate, right? So because of whole conjugate, here you will get minus conjugate of this term, it becomes 2 minus j. Conjugate and conjugate becomes cancel. Here you will get x2 plus 1 minus 2j conjugate becomes 1 plus 2j. Conjugate of x1 and this whole conjugate becomes x1 plus w2 conjugate. The same equation I am written here. Right. So again, I want to write x1 coefficient first, then x2 coefficient. Now I want to represent the second instant received symbol y2 conjugate is equal to, okay, 1 plus 2j minus 2 plus j into this vector plus y2 bar. Now this is the second equation, and here y1 is the first equation. I want to combinedly write these two equations as a vector, received vector. This is received vector y bar. Here MISO coefficient vector, efficient vector, okay, and this is transmit vector. Here this is noise vector, right? Noise vector. Now after finding this one, here we have to check orthogonality. Orthogonality is checked by C1 Hermitius with C2. This is C1 Hermitius value and this is C2 value. So by multiplying this one, here the resultant is 0. So that this C1 and C2 is orthogonal. Therefore here C1 and C2, these two coefficients are orthogonal. So it is orthogonal means it is orthogonal space-time block code. Now coming to decoder, here we have to find C1 Hermitius with norm C1 with y bar. C1 matrix, C1 norm will be represented like this one. Its value is root 10. Okay, and here I want to substitute this C1 norm value. So by putting the C1 Hermitius, C1 value is this one, C1 Hermitius, transpose and conjugate. Okay, this is C1 Hermitius and it is, okay, y bar vector, and here it is norm C1. The resultant is extraction of x1. By expanding this equation, you will get that one. Similarly, for extraction of x2, so wherever the C1, just I am putting C2 Hermitius. So here you will get extraction of y2, so x2. Okay. Now there is another problem we can discuss here. Consider 1x2 MISO system with Alamouti coded transmission. Signal to noise ratio is 25 dB. What is its bit error rate? Right, in the code, in the problem, they are given signal to noise ratio in dB format, as well as is asking to bit error rate. So average bit error rate, not bit rate, this is bit error rate, that is the BER is represented by 3 by signal to noise ratio square. Now I want to convert this signal to noise ratio dB to normal value. So that is happened by using this equation 10 log base 10 SNR is equal to 25. Okay, log SNR base 10 is equal to 25 by 10 becomes 2.5. SNR is equal to 10 power 2.5. Now bit error rate BER is equal to 3 by SNR square. 3 by, here we can write 2.5 whole square. So it becomes what? BER is equal to 3 by 10 power 5. That is equal to 3 into 10 power minus 5. Right? Okay. Please practice this derivation for external exam point of view. Okay. Don't neglect to practice this derivation. It is a very, very, very important one.